Last talk of the day. See how this goes. So I'm going to talk a bit about tracing and what's happening in the virtual machine, the things that were the status of it today, and what's going to happen in the future. My name is Lukas. I've been here a couple of times before speaking. I work at Erlang Solutions. I've been at the Erlang OTP team at Ericsson as a consultant for the last, 5, 6 years. I lost count for a long time now. I work with the virtual machine, so doing things there. For the last, 3 months, something like that, I've been working on doing changes with in regards to tracing and the support of the tracing in the virtual machine. So by now, I think I've changed every single line of code that has something to do with tracing in Erlang there. And today I'm going to talk a bit first about an overview of tracing and go through a bit about the different things about tracing that you might know and some of the things that you might not know. So I'm going to go through all of the things. Then I'm going to talk more about what's happening in Erlang OTP 19, the different changes that I'm introducing in there for different reasons. And also the work is continuing going on in Erlang 19.1, 19.2, and 20, and so on and so forth, and a bit about what I want to do with tracing then. So let's talk a bit about tracing today and what the different things and what's bundled into the whole tracing framework that we have in the virtual machine. So the tracing stuff, I pulled this quote off of Wikipedia. It's a specialized use of logging, so you have a dynamic logging to try to debug your application as it's failing in a live environment or in a testing environment to get information out of what's happening there. In Erlang, tracing support is built into the virtual machine, and it has been from the beginning, as far as I know. You can trace on state changes of the processes. You can trace on message passing, things happening in the system. You can trace on function calls. You can trace on a lot of different things inside the virtual machine. And you can decide where you want these traces to be sent. You can send them to a file, to TCP, to standard out, and to a process, lots of different things. The general setup is something that, at least for me, it just sits and I just do it. It happens automatically. You start a tracer with DBG. You say, oh, all processes call, and then you say, I want to do it on list sequence, and then you call list sequence. And then you follow the different steps. You say list sequence 1A, and then you see that it's called, and it crashes, and now you understand what's going on. And then this is, of course, something you can do in a live system as you're monitoring and so on. So that's the basic idea of it. You kind of instrument your code lively to see, so you don't have to do IO formats everywhere. And personally, I use this when developing all the time. So IO format things in the code is not something that I do. We have another part of the tracing framework. That's the trace receivers, so the things that are receiving trace messages. So they kind of decide what happens when a probe is triggered. So when we've decided that we want to generate a trace message for a function call, for instance, we have different options. And this is when we're talking about what's in the virtual machine today. So we have two options that we can work with. Either we send a message to a process, and that process can decide what it wants to do with it. So one of the most standard ways of doing it is that the process prints it to standard out so that you get a message in there. The process could also do some kind of analysis to see, okay, so for instance, the tool fprof uses tracing on call traces in order to kind of simulate the stack of a process. So when it receives a message, it says, oh, now you're here, and then it calls, and then it builds a simulated stack for each of the different processes running in the Erlang virtual machine, and you do profiling events because of this. So you can have them doing lots of different things. You can also send a message to a port, but now you get a message that's converted to the Erlang external term format, sent to the port, and then you can write it to a file. You can write it to a TCP socket. You can do whatever you want to do. So you can write your own port that just follows a very simple protocol, and you can output it to whatever you want to output it to syslog, to dtrace, to systemtab, to whatever you want to do. Built into runtime tools, there's two things, and there's file and TCP, but it's possible for anybody to write anything. And this port interface is much more efficient than the process interface to work with, as it doesn't have to do the same things. So the different kinds of tracing events that we're talking about is for a process, there's a lot of meta state that moves around that I find is quite useful when debugging what's happening with processes, and there's also intermixed with the different calls. So you have a guaranteed order of the trace messages as you pass through a system where you can reason about them afterwards, so you can see that logically that these things are happening. So if we execute this small function up here and we start tracing at when we receive the go, we will have a couple of trace messages. We're starting with receive, and then we get scheduled in. So we receive the message, we get scheduled in, we call the list sequence function, then we return from the list sequence function, we get scheduled out, and then we get scheduled in again at the time later, the timeout is triggered, and then we exit the process. And we can track all of these different events using different probes inside of the virtual machine, and all of these can then be sent, of course, to a process or a port, depending on how you configure it. And this is, you can configure these trace events on a emulator level, and then you can say which processes you want to trigger these events. So you don't have to trigger them for all processes in the system. You can say that, okay, I only want to have this subset of processes triggering these kinds of events and tracing them in different ways. So it's the intersection of all of the traced processes and then the traced modules when it comes to call tracing that generate these events. Meta tracing. So meta tracing is another feature that's not very well known. I think the original name comes from being able to extract metadata out of the runtime system in parallel to normal tracing. Not really sure about it, but I think that's it. What it does is that it introduces a second tracer into your system that's global instead of being process-specific, that you can trace function calls on. So it sends, you register a per function tracer that you know that all of the trace message, all the calls to that function will generate a trace message to another trace process. I'll give an example. So we can just start GBG and we get the tracer, and you enable it using the BIF, Erlang BIF, so you do Erlang trace pattern, gen server cast, and then you do the meta tracer. So you add an option to the trace pattern saying this is a meta trace. And we see that it matches one function in the gen server cast. And then without having to turn on any tracing on that process, we get a trace message from that call when we call that process. So when we send it to that gen server cast to ourselves, we get a trace message. So this is kind of orthogonal to the normal tracing where you have per process, and it's normally used for tooling in order to understand what's happening in the system. So it's kind of used in order to figure. One of the use cases I know is that you put a trace on register and unregister so that you know which processes have which names so that you can resolve that in tooling and so on. And there's other use cases for it as well, and I will show some of them later on. So match specifications is also part of tracing. So match specifications are used in ETS and in tracing. And in tracing, it's used to filter different events. Now, match specification is kind of an acquired taste, and you need to do a lot of acquiring before you get a taste for them. I think I've gotten there, possibly. I'm not sure. I will go back and forth on it. So it's there in order to discard events early or change the behavior of the tracing somehow. So you want to generate some extra events, create some extra data, attach some extra data to the trace message or something. But normally, the use case is in order to decide not to do a trace event or when to do a trace event, depending on different scenarios in order to not overflow the trace system. So it looks something like this. So you have these smiley faces looking up here. So you have the function argument match. So that's basically saying, when a function call happens, these are the things that I want to check, and it's a list of the arguments. So in this case, we have a tuple in the first. That should be a two-tuple, and then we have an unknown, and then we bind something to the third argument of the function, and we check that the length of the list that is in that argument is equal to 1, and if that is the case, we generate a return trace. And if this does not match, then we don't generate a trace message at all. So we kind of filter down and say that we're only interested in having trace messages when this condition occurs, because that's when we know that something is wrong. Let's see, guard clause. And then there's an implicit message true action that always happens when you kind of generate these match specifications there. And that says that it should generate a trace message. You can say message false, and then it will execute this match specification for its side effects. We'll get a bit into what the side effects might be of a match specifications. So combining meta tracing and match specifications in some clever ways, you can work with systems that have a lot of load on them and get snapshots that are quite accurate and low overhead of what the system is doing at that time. So an example here. So we set a trace pattern on genServerCast. We only want to generate a trace message when it is ourselves that's calling it. That could be another PID, but that's what we want to check there. And we want to modify the tracing state of the process that calls it. So this is a kind of function in the match specification. So it says enable tracing and put on send tracing and use the tracer T as the tracer for this process. So it will put on the send tracing for that process. And and we use it as a meta trace. So whenever this function is called with anybody, that's what it's going to execute. And then we add this extra logic in here saying that, OK, so now we're going to enable tracing when this function is called for this specific process that we're executing here. And you can have quite complex guards saying that, OK, so if the second argument is a list with integers, blah, 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 and so on in order to do it. And then when we call genServerCast, we get a trace message for the genServerCast. And we get a trace message for the actual send to ourselves as well, without having to set up the send part. And then we can add, if we want to, the message false part of the meta trace pattern. And then we don't get the trace message for the meta trace. We only get it for the actual trace that we were interested in. So we get only the trace of the sending message. Let's see. Yeah, so there's a couple of functions in match specifications that you can read about in the documentation that I use a lot when I'm trying to do complex match specs and trying to do complex tracing scenarios. And one thing is the trace control word, which is very nice. It's a one-word 32-bit integer thing that you can read and write from match specifications, and you can also read and write to it from Erlang code. So you can use this to kind of guide your match specifications to say that now I want to do a snapshot, and then the match specification, you set it to 1, and then you do a tracing, and then the match specification immediately sets it to 0 again, and then you kind of do sampling of what you're tracing with very little overhead. And then you use enable and disable trace in different ways to enable the different trace flags on the processes. So a complex example would be something like this. So you can get the, let's see if I can hear there. So you get the trace control word, and you compare it to 1. And if that's true, then we set the send flag on the process, and we don't do a message. If it's not equal to 0, we send it to false. So the first time I spawn this process that does list sequence here, it's set to 0, so we don't get any tracing on it. And the second time we call it, we set the trace control word, and then we do the tracing, and then we get a trace message for it. And then the next time we call it, we won't get it again. Oh, actually, we will get it again here, as we didn't reset it. But we can do that as well. So different combinations of this, you can do different useful things. So match specifications and meta tracing. So there's another part of tracing called sequence tracing that you use in order to trace events as they pass by messages between processes. So you kind of follow the events as they pass. So you say that you set a token on one process, and then that process token will be passed on and incremented as it gets passed to the next process, and then to the next process, and then it's cleared when the process replies. So you can do these things, and you can interact with them in match specifications again, and you can interact with them in meta match specifications. So all of these things work together. It also works over distribution, so you can send over distribution in order to say that, okay, I just want to see the consequences of this specific function call happening in my system. We also have dtrace system tab support in the virtual machine. There's been a lot of talks about it, so I won't go into much of the details. We have tracing on ERT events and of Erlang user space events. So there's probes for almost all of the normal use trace events that you can do in Erlang tracing. There's for dtrace system tab. And you can filter them using dscripts or stab scripts. And you can correlate them to external events and so on. Very useful. So this is kind of the scope of the things that I was looking at in, I don't know when it was in November, when I started looking at this and trying to see, okay, so what are the most important things that we wanted to change? And I had a discussion with lots of people from the mailing list and trying to figure out what exactly should I be focusing on. And there's also the requirements coming from within Ericsson about what the different things are in there. So I'm going to go through the changes that I've done and the different things there, and then I'm going to talk a bit about what's left to do. Unfortunately, there's still left things to do. Work is never done. So the first thing that I've been focusing a lot about is performance, and especially like performance of tracing as you add more cores and work with larger data sets and more load of the different things. So one of this is the architecture kind of what the tracing system looks internally in the Erlang virtual machine before 19. So you have a bunch of processes that are generating trace events. All of the different trace events are being put into a global queue, which is protected by mutex, and then they are consumed by a thread that's called the system message dispatcher that consumes all of these different things and routes them to the correct process and port. Now, this may seem terribly inefficient because we kind of have to route everything there. Why don't the processors send it all the way to the process or port from the beginning? And indeed, let's see, the reason for that is something that's called a global lock order inside the Erlang virtual machine. So I'm going to try to explain what that is briefly. Let's see how briefly it is. So in order to avoid deadlocks within the Erlang virtual machine, we have what's called a global lock order, which means that there's a defined way for every mutex to be taken within the virtual machine, so that we know that we can only take locks that are of lower priority than the ones we already have. And there's a whole mechanism of how this is implemented and verified within the virtual machine. So the general idea is that the port lock is the highest priority, and then you have the process main, and then you have the proc link, and then you have the process messages, and then the process status, and then there's a bunch of Ertz internal stuff. And this is not a complete truth. There's some other locks intermingled in between there. In total, there's about 90 locks that you have to keep track of in different ways. And in between processes and ports, so you have a main lock of a process 1 and you have a main lock of process 2, there's also an internal ordering for these ones, so that if you have a PID 1, you're only allowed to take, or actually if you have PID 2, you're only allowed to take locks of PID 3, 4, 5, 6. You're not allowed to take the main lock of PID 1. So then you have to release the lock and take the other lock and then take the original lock. And that screws up all kinds of guarantees about what data structures you're protecting with the different locks. And the problem here was that message passing, so sending a message to a process, is protected by one of these locks. And when we're doing tracing, we need that lock to be protected. So we couldn't take the message lock of the process that we wanted to send the message to while still keeping the process message lock of the sending process, of the process that was being traced. Because then we might end up in the deadlock. And this simple solution that we did when just starting up with the SMP support was to introduce this thread with a very low priority on that lock, so that we could just place that lock in the queue, and then that other thread could take the locks of the processes, and everything was fine. Let's see, should come back soon. I hope. It's coming. Yay. So we had a problem there. And that was solved in that, and it worked fine for the scenarios that we were using then. And it's kind of been pushed along as we've been doing releases, but now it was time to do something about this. So in 19 now that I've removed the need for the status lock to be taken, so we only have to really care about the process message queue lock in order to order events. So the ordering of the events is very important, and you want to be able to see that the trace events arrive in the order that the code was called so that they're not reordered for some reason. And some of the code needed the status lock in order to order things like the process exiting and exit signals being sent to other processes and getting that order correctly with other events that are happening in the system. They needed to have the status lock taken, but I removed those part of that. And we're only left with the message queue lock, and I need to have that message queue lock taken in order to order the events. So I had to work around that somehow. And the way you work around having the lock order is by using something called a try lock. So you try to take the lock, and if it's already taken, you have to do an asynchronous operation of some sort with the tracing. You have to deal with it, and we cannot spin because it could be taken forever, or we could actually be deadlocking ourselves. Because when calling these trace events, we don't always know which locks we have, so we might be trying to take a lock that we already have in the same thread, which causes all kinds of havocs. So we have to do a try lock in that way. So in order to achieve this, there's been an introduction of a per process trace message queue that's completely internal. You can't inspect it from the outside, but it uses a lower priority lock. And whenever you get a failed try lock, you will take the process lock and then you will put it into the queue instead and start accumulating trace messages in that queue. And that lock has to be taken every time you generate a trace message. But this is much better because now we have a distributed system and we're taking locks all over the place rather than having one place where we're taking one lock and having all of the different schedulers contending on one lock. So the general algorithm is something like this. We take the proc trace lock, we check if the queue is empty or not empty. If it's not empty, then we just add it to the tracee's trace queue immediately. We don't have to. And then we just have to queue things because we need to order the events so that a function return does not come before a function call, or a send doesn't come before a send that you know is after. So you have to order all of these different events and keep causality in the events intact. And then you unlock all the locks. If it is empty, you try lock on the remote message queue. And if you succeeds, you just put it in the remote process's normal, so the tracer's message queue box. And if it's busy, you put it in the queue, and you schedule a flush event. So you schedule the process that is the tracer to flush all of its trace queues as soon as possible. And that kind of makes it so that it will generate these trace messages almost immediately. And the normal scenario for this kind of contention to happen is when that process is actually running already. So we schedule it to say that, okay, when you're scheduled out, the first thing you're going to do is you're going to flush your trace message queue box. So now we end up with something that looks like this instead for the architecture. So we're sending directly from the processes to the processes, with the different traces or to the ports, which turns out to be quite performant. So some of the functional impacts that you will see when you're using this tracing, because this is it breaks a global ordering that was there before that we didn't really guarantee, but it was always there. So trace messages are much more likely to become out of order with normal messages. So what that means is that if you send a message to the tracer process, and then you expect the message for the send trace and the actual message you send to that process to be in a certain order, that's not guaranteed anymore. And it has never been guaranteed, but it's been very, very likely that it will happen like that. It's very unlikely before 19 that it will happen. It will be much more likely in 19 and afterwards. Timestamps will most likely arrive out of order as well. So you will get events that are generated by timestamps, and they will, in the timestamps, arrive out of order because we're queuing things in the different processes. And the timestamp is taken when the message is generated, and then it gets queued, and then it gets delivered to the tracer later on. So the timestamps will not be in order. But the events will be logically in order, so you can't, so events from the same process will be internally consistent, and when you're communicating in between processes, they will be internally consistent. So if you have a send from one process and then a receive on the other one, the received trace message will be consistent with the different parts there. But it will be noticeable, these things. Of course, not if you... And the port stuff kind of still works the same way as it does before, so the ordering things works the same there. It's just when you're tracing to a process that we have these issues. There we go. So I did some benchmarks on this, so let's just go ahead. I ran 10 processes on my machine. I did 1,250 ASIN1 encodes. That generates somewhere in the region of 7 million trace messages. And you measure time. I measured time until the benchmark completed, and I measured time until all of the trace messages have been delivered to the tracer. And I also measured the total memory usage during this time. So as a baseline, this is just a benchmark running. And the red is 18.2.3, and the green one is my private branch. And we can see that, well, 19 is faster than 18 even without my changes. Good stuff. So I didn't have to change anything to make it faster, which is always nice. I think this has mostly to do with some optimizations in the compiler that's doing this. So the ASIN1 encode has actually gotten faster, which is good. So call tracing to processes. So if you do this thing and you send messages to the call tracing over different schedulers on the x-axis, we get a speed up of somewhere in the region of, I don't know, 2 times, 3 times faster. So this is for the overhead of the call. So this is when the process is running, how long time does it take to complete. So the overhead of tracing is about that much. So that's neat. If we add how long it takes for trace messages to be delivered to the receiving process, it's about the same there. So for processes, when we're sending messages to processes, it's about the same. We still have about a 2-3 time speed up of everything. If we do arity tracing on processes, so if we do call arity, so we don't care about the arguments, so we have much, much smaller payloads that are being sent, we get a better increase, a much better increase. I'm not sure how much that is, but it seems about 5-6 times better. So we're handling small trace messages much better than we did before, but the larger ones, kind of the overhead of copying the entire payload of the message kind of overshadows everything else in there. If we trace to port, now port apparently was very bad in 18. So we have this linear curve where it just goes up and up and up and up. And for the new code, it's kind of like just flattens out and rises slightly. And it's like 412, yeah. So it's quite a decent speed up for that as well. And call arity, small messages, not as big a difference. Here, apparently, it's better when you're tracing small messages to a port than if you're doing it to a process. Memory usage has gone down quite a bit as well. So in 18, we're using about, 7 gigabytes when calling to the process with the process. And then we fall down to about 4 in 19. And when we're doing arity tracing, we're about at 4 gigabytes of memory usage when we're running the trace, the old one. And then we're about, 750 megabytes. So improvements all around, except for port tracing, which is the opposite. So for port tracing, we're having the memory usage is kind of growing. It's not growing a lot, so it's at about 3 gigabytes or 2 gigabytes. But in the old implementation, it was so slow that it wasn't possible to generate enough data for it to actually use any memory. So you kind of end up with no memory usage, which is a good thing if you're on a low memory system. But I mean, the overhead kind of ruins the usage of tracing at all. So it's, yeah, not a good thing. So that was the performance scalability things. So one of the other things that's coming in 19 is something called tracer modules. So right now you can have, as a trace receiver, you can have a process or you can have a port. In 19, you're going to be able to have callbacks and a module as the trace receiver, so that you don't have to copy messages onto other stuff in order to make decisions about what's in the different messages, or you can plug in different backends to your different things. So tracer modules are there in order for you to be able to do earlier filtering to kind of complement or / replace match specifications as the earlier filtering mechanism. You're supposed to be able to have pluggable backends that are much more efficient than routing everything through a process or a port, so that you can do with syslog, LTTNG, you can build a sampling profiler on top of this, or lots of different things. It's very performant, as you are called directly in the context of the original process when you're doing that. And hopefully you will be able to write Erlang code to handle this tracer. So you enable it with something like this. So for all new processes, I want to do send tracing, and instead of doing tracer PID, as is the normal one, you do tracer module and then a state. The implementation is quite simple. So you have an enable filter first that says that, okay, so which trace points do I want to care about? What should I do with them? So there's 3 things you can return. You can do trace, you can do disable, or you can do remove. So if you trace, then the trace callback will eventually be called, not immediately, because the enable check is done a lot earlier in the call stack than the other stuff, because we have to do a lot of fiddling around before that. And then the trace callback is called, and then you have the event type, and you have your tracer, which is the state, which can be any custom state that you put in. And you have who is being traced, the message, and the to in this case, because it's a send trace. And then some options that have been supplied by the tracer, like if you want timestamps or if you don't want timestamps. And all of the port and process tracers that I showed you with the benchmarks, they are written using these callbacks. So the performance is still there with this new API, which is kind of nice. One of the bad things about this with the 19 release, unfortunately, is that they have to be NIFs, all of them. So you have to implement your Erlang code as C code in the first release. In later releases, some of the events, most significantly call, will be able to be run in Erlang code, but things like internal state changes of these schedulers and things will most likely always have to be native C code that you do things with. But just having it for call tracing, I think, will be great to do lots of different cool stuff with it. It handles all trace events, so trace events and sequence trace runs through these modules. In 19, there will be a process and a port tracer, and there will be a dtrace system tap LTTNG backend for these tracers that will run through them in there. And that's one of the major reasons that we did this, is in order to have LTTNG support for these parts, because we do a lot of stuff with LTTNG at the moment. Let's see. After 19, yeah. So hopefully you will be able to do more of it in Erlang code, and you don't have to program C anymore. We will most likely move system profile, system monitor, and other kind of events to the system as well. We want to have specialized backends for specialized purposes. So if you want to build some kind of, my idea is to build some kind of sampling profiler and feed it back into Scott's eFlame thingy to make it the overhead less, so that you can figure out things with all the goodness of sampling and badness of sampling. that you get. Or load shedding, so you automatically realize that you want to do things or send stuff over UDP. Lots of different backends that can be efficient in manipulating this data in different ways. We're also adding more match specifications, more ways of doing match specifications. Let's see. So one of the things that we're doing is that we're putting in the ability to do match specification filtering on send. So whenever you send a message somewhere and generate that trace message, you can do tracing on it. I'm not sure if it's visible, but this specific match specification filters so that it only generates trace messages if you do a send to a remote node. So it kind of keeps it in there and figures out which processes are communicating over the distribution channel. And we're also doing it for receive the same way. So in order to figure out different ways and filtering on send and receive tracing in different ways. And this specific one is that it only generates trace messages when a gen cast arrives in the mailbox. In the future, depending on how successful the trace module things is, we will either add more match specifications or make the trace module thing more powerful. We'll see what happens there. So that you can filter on other things like state events of processes and all the things you want to. There's also been added support to do better introspection of ports, so port tracing. So there will be, when you do enable tracing, if you do Erlang trace new ports, for instance, you will trace on all of the different ports and all of the different things that they do. So you can do send and receive tracing on ports and the ports events themselves. So if I start something up like this, and then I open a file, we can inspect under the hood what's happening with that file, the different messages that get sent to and forth the port, and all of the different things happening there. And we can see that, okay, when I do an IO format to that port, that what actually happened is that it sends a command with a 4 and a hello world, and then it gets a reply back with a data, which is kind of the status code of that thing. And when I close it, I send a flush command, and then I do a port close, and then we get all of the different link events and so on. So it's kind of completing the entire tracing things for everywhere. So my vision of what I wanted to do before I started out this is that I always want to do more stuff than I actually have time with in different places. So I wanted to focus on, these were the feedbacks I got from the community and the things that I wanted to do myself. So I wanted to focus on flexibility in order to get multiple tracers working, earlier filtering, overload protection of tracing events in different ways. Wanted to make the documentation better, so do a more, basic DBG interface that you can work with, better describe the DBG TTB interaction, and also make match specifications less scary when you're using them. Integrate better with tools, so LTTNG, dtrace system tap are all tools doing the same job basically. Possibly get into the common trace format groups and integrating with the Eclipse trace viewer thing that it has to view events. And look at performance, so the overhead of the actual program that's running and the scalability on cores as it's running through and the throughput of trace events as it's going there. So what I've done so far is that the early filtering, the match specification documentation, the LTTNG dtrace system tap stuff, and the overhead and scalability is kind of there, and it works, and it's great. I've built the framework to fix the overload protection, the common trace format, and the throughput business. So hopefully that will be kind of either the community, let's hope, builds these things, or I will have to do them myself eventually, in order to build on top of the tracer modules and the different trace events that we have. And the things that are to be done yet is the multiple tracers or trace sessions or whatever you want to call it. And that's, at the moment, highest up on my to-do list to do. I don't think I will have time for 19 to do it, unfortunately. But it's going to come. Question is, if it's probably going to be 20 then if it's not 19. We'll see. And then a bit more documentation work needs to be done in order to finish this stuff, and hopefully that will be in 19. We're continuously working with improving documentation in different parts here. Yeah, I think that was it for me. Any questions? Yes?
Can you say anything at all about the overload protection?
The details about exactly what I'm going to do there, I'm not sure yet. But of course, the way like Redbug or all of the different debugging tools is that they kind of measure how much message input you get and so on. And the part of the overload thing, I guess, is just turning it off more efficient and earlier and having built-in support into the libraries instead of having to rely on third-party things to do it. It's the general idea. So I'm going to steal ideas from other people and put them into OTP. Okay, thank you.